Greetings, physicists. This video will be about problems involving an electric field or multiple electric fields. So we'll start with this, with an atom. We saw this back in chemistry. You have a hydrogen atom, which is a proton, and an electron. And the electron in the Bohr model was said to go around in a circular orbit. And you eventually learned that was not quite true when you got to quantum theory. But we're going to pretend that the Bohr model is accurate enough for us. We know the radius of that atom. It is that many nanometers. And we're curious, what is the electric field? Due to the proton, right? Because protons are positive and electric fields go out from positive charges. So if we were to put an electric probe at this point right here, what would it read due to the proton? Now the interesting part about this is you don't need to know anything about the electron, other than that it orbits at this radius. You don't need to know its charge or mass or anything to solve this problem, because the field is only going to be based on the proton. So if you ever forget the electric field equation, just start with the Coulomb's law equation. That was F equals K QQ over R squared. And then recognize that we're trying to eliminate the electron. So the electric field is when you divide both sides by Q. The Q of the charged particle on the outside anyway, not the Q of the field generator. So that will get rid of one of the Q's, and you will get this equation, that the force divided by the charge, the Q test we call it, is equal to the K Q over R squared. Or we just call that the electric field E. So we really need these things. We could calculate it using the force in the Q test, but that's not what they gave us. They gave us an R. We know K. So what we really need to solve this is the charge on a proton. Usually this will be given to you on a test. If you're in AP, this will be given to you on the AP test. In fact, it's on your formula sheet, but I'm going to Google it right now. Charge on proton. Plus 1e. No, that's not what I want. But there it is in coulombs. Okay. So it's 1.6 times 10 to the minus 19th. Positive. Alright, so I'm going to plug in all those things that I know. I know K is 9 times 10 to the 9th. I know that the charge of a proton, or at least I just looked up, is 1.6 times 10 to the minus 19th over R squared, and the radius was, I think, 0.053 nanometers. Let's look. Yep. All right. 0.053. A nano is a 10 to the minus 9, so times 10 to the minus 9. And I'm squaring that, but before I square that, let's just move this over twice to make this. I'm going to go ahead and erase that and just say that this is 5.3, and we lost 2 tens doing that, so that's times 10 to the minus 11. Alright. I'll deal with the tens first. I have positive 9 of them and minus 19 of them, which leaves me on top with minus 10. I have minus 11 on bottom, so I lose all the ones on top, and I'll have minus 1 on bottom. And to bring that up to the top, I just change the sign, and so that becomes a positive 10 to the first on top, or really just 10. So, rewriting this, 9 times 1.6, that 10 is on top, divided by, oh, I forgot that this was squared. So I will still have a 10 to the minus 11 on bottom, and this is squared. So pop those 10 to the 11s up as well. So there's going to be 12 tens on top. All right. Just making sure that's okay. Yeah, that looks right. So, can I scroll? That would be great. On bottom, so I'll have that on top, and I'll have 5.3 squared on bottom. So let's do the calculator real quick. And we get 9 times 1.6 divided by 5.3. Oh, come on. 9 times 1.6 divided by 5.3 divided by 5.3, and I'm getting this 0.51 times 10 to the 12th, and if I move that decimal here, that's times 10 to the 11th, so 5.1 times 10 to the 11th, and when we do electric field, it's newtons per coulomb. So that is the electric field due to a proton at the position of an electron. Pretty straightforward calculation. All right. Scroll. There you go. More trouble scrolling than anything else with this app. All right. We're a ranking task. Love me some ranking tasks. We have 4 sets of charges and distances. We're saying who's got the biggest field and who's got the smallest. Looks like we're changing Q and twice the Q and R and twice the R. So who's going to have the biggest field? Well, remember KQ over R squared. R is on bottom, so the bigger it gets, the weaker the field gets. Q is on top, so the bigger it gets, the stronger the field gets. So the thing that has the biggest electric field will have the largest charge and the smallest R. So B is definitely going first. The one with the weakest field should have the largest R and the smallest Q. So C is going to be at the end. So now we need to compare D and A. Well, going from A to D, we gain twice the radius and twice the charge. So that's 2Q on top, but that's 2R, and we're squaring that on bottom. So we're actually getting 4 times as much on bottom as we get on top, which means that the one with the bigger radius is going to be smaller in terms of its charge. And so I'm going to put D right there. I'm going to put A right here. Now we should probably actually compare D and C. No? No. That's fine. I was looking to see if any of these should be equal, but I don't think that's the case. Right? We go from I don't think that's going to be the case. Okay, so onward and onward. Last one. A dipole has a positive charge and a negative charge, and they are the same magnitude. That is the definition of a dipole. They have to have the same magnitude, and they have to be opposite in charge. And these 2 charges are not on top of each other, otherwise they would cancel out, but they are separated by this distance. And we are curious what the field strength is outside of the positive charge by 1.2 centimeters. So let's draw this. Let's put a negative charge here. Let's put a positive charge here. We are along a line connecting them. So here's the line that connects them. Pretend it's a straight line. At a point that's 1.2 centimeters outside positive. So I have to be over here at this point. So that's the point I'm probing. What am I looking at? Field strength. They are separated by 1.2 centimeters. And this is a separation also of 1.2 centimeters. Okay. Well, so that's interesting then, because both charges have the same magnitude, and also this charge here is at, the positive charge is at some distance r, and this negative charge is at some distance 2r. So the negative charge should have, right, 1 over r squared, so 1/4 as much force, or 1/4 as much of the field as the positive charge does. So the electric field goes out from positive charges and in towards negative charges. So at that point, we should have the field from the positive charge minus essentially 1/4 of the positive charge. So we're going to have 3/4 of the field produced by the positive charge at that point. But let's put some numbers to it. I'm just going to calculate the positive charge and multiply it by 0.75, essentially. So again, electric field strength will be KQ over R squared. We know K is 9 times 10 to the 9th. We know Q in this case is 1.5 nanocoulombs, 1.5 times 10 to the minus 9, over, we have R on the bottom is 1.2 centimeters, or 1.2 times 10 to the minus 2, and we're squaring that. So this squared will be minus 4 on bottom, minus 4 tens. Oh, and there's all the tens on top cancel. So if it was minus 4 tens on bottom, it's going to be positive 4 tens on top. And then I just have to go 9 times 1.5 and 1.2 squared. So 9 times 1.5 divided by 1.2 divided by 1.2. And what does that come out to? I get 9.4 times 10 to the 4th. 9.4 times 10 to the 4th newtons per coulomb. But I have to subtract from that the negative contribution of this field, which is 1/4 of that field. Well, 1 minus 1/4 is just 3/4. So I could also just take this number and, again, like I said, multiply by 1/4, or 0.7, or 3/4, 0.75. So take that number times 0.75, and I get almost exactly 7. 7.0 times 10 to the 4th newtons per coulomb. That's the leftover field at that point. And it would point to the right. So you definitely want to include a direction. So the field at the point indicated is 7 times 10 to the 4th newtons per coulomb to the right, this direction. Okay? Hopefully this is useful for you in calculating the electric field.